Hello, today we're going to talk about the central limit theorem for sums. It's a lot like the central limit theorem for the means, but we're just going to do it with sums. All right. So suppose we have a random variable x with a distribution that may be known or unknown. Just like with the means, it can be any distribution. And suppose mu sub x is the mean of x and sigma sub x is the standard deviation of x. Then, if you draw random samples of size n, as n increases, the random variable that is the sum of all those values in the sample, consisting of sums, tend to be normally distributed. So that random variable is normally distributed. The mean is the number of samples times the old mean, and the standard deviation is the square root of the number of samples times the old standard deviation. So the mean is equal to the original mean multiplied by the sample size, and the standard deviation is equal to the original standard deviation multiplied by the square root of the original sample size. Let's do an example. We have an unknown distribution, but we do know that it has a mean of 90 and a standard deviation of 15. A sample size of size 80 is drawn randomly from the population. So we want to find the probability that the sum of the 80 values, we add those all up, is more than 7,500, right? So what do we need to do first? Well, we're going to set up a random variable first. First, we're going to let x equal one value from the original unknown population. That's a random variable x. And the probability question asks you to find the probability for the sum. So what we need to do is we need to find a new random variable that's the sum. All right, so that's our x. Sum x is our random variable that represents the sum. What we're going to do now is we're going to calculate the mean for the sum. And that's going to be the number of the sample size that was n, remember that's 80, and our old mean from the original distribution, which was 90. So the mean for the sums is 80 times 90, which is 7,200. The standard deviation for the sums is going to be the square root of n times the original standard deviation. So that's the square root of 80 times 15, which is 134.16. And now we have these two values. We know that sum x is distributed normally with a mean of 7,200 and a standard deviation of 134.16. So if we want to know the probability that the sum is greater than 7,500, we just use Desmos, and I'm not going to bother to pull it up here. You guys have done this a lot at this point. A normal distribution, we put in our mean and our standard deviation. We find the cumulative probability distribution function. We want to know 7,500 to infinity. That's this area right here. What's the probability of being higher than 7,500? And that's going to be 0.01267. So pretty small percent. So let's recap what we did. We wanted to find some probability about the sum of these 80 values. So we calculated the new mean and the new standard deviation for the random variable that is the sum, and we used the normal distribution calculator in Desmos. Let's try another example. Let's find the sum that is 1.5 standard deviations above the mean of the sum. So actually, we're still in the same example that we are. We're just doing another question on it. So what sum would be 1.5 standard deviations above the mean of the sums? So what we're saying is we want the mean of the sums, which is here, right? That's mu for mean of the sums, plus 1.5 standard deviations. And we know a standard deviation is root 80 times 15. We want 1.5 of them, so we multiply those by 1.5, and we can see that the number, this sum, 7,401.2, would be 1.5 standard deviations above the mean for the sums. So that's a calculation that people want you to do sometimes. When you're doing that sort of a calculation, you're just going to use mean plus z-score, right, of 1.5 times your sigma for the sum. All right, let's try another example. This is one for you to try. The mean number of minutes for app engagement by a tablet user is 8.2 minutes. Suppose the standard deviation is 1 minute. Take a sample size of 70. What are the mean and standard deviation for the sums, right? So we're going to do a sample size of 70 and add them all up, all right? So I want you to pause the video, and right now, pause the video and find the mean for the sums and the standard deviation for the sums. All right, so what we did is you just did 70 times the original mean, and that gave me 574 minutes. And for the standard deviation, you did root 70 times the original standard deviation of 1. That gave me 8.37 minutes. So now we know that the sum, x, is distributed normal with a mean of 574 and a standard deviation of 8.37. All right, let's do another example using our inverse functionality on the normal distribution. So the same example, different question. It's a tablet user's engagement is 8.2 minutes. The standard deviation is 1 minute. Take a sample of size 70. So we still have the same mean for the sum and the same standard deviation for the sum that we had in the previous page. But now I want you to find the 95th percentile for the sum of the sample. And let's interpret this in a complete sentence. So we want to know the 95th percentile. Here's our normal distribution for the sum, right? This is for the sum of x. Remember, when we use inverse CDF, you give it the percentile. So that's the 95th percentile. And it gives you back the value that would be at that 95th percentile. So that means that 95% of the values for this normal distribution are below 587.76. So as in a complete sentence, we would say 95% of the sums of size 70, 95% of the time, the sum will be below, let me repeat that, 95% of the time, for a sample of size 70, the sum of those 70 values will be below 587.8 or whatever it is, minutes. All right, let's find the probability that the sum of the sample is at least 10 hours. Same sort of example that we're doing here. We have the same normal distribution of 574, 8.37. We just use the straight up Desmos to calculate this. We want to know that the sum of the sample is at least 10 hours, which is 60 minutes. This is one that you need to be a little bit careful on. Remember, we need to change that to minutes because this is in minutes and this is in minute. Oh, that's not minutes, that's numbers. 8.2 is in minutes and the 1 minute is this standard deviation. So these units are minutes. So we need to make sure that if we ask about the probability, those guys are in minutes as well. And that's the only tricky part about these kind of problems. The probability that it's at least 10 hours is the probability that 600 minutes or more, and that's a pretty small probability. All right, well, that's it for section 7.2. It's really just a lot the same as with the means. When you take the sums, you just have a new normal distribution that has a new standard deviation and a new mean, and you just do the same sort of computations that you've done in the past.